Okay, receiver structure, the basic super heterodyne. What's heterodyne? We covered that, eh? Heterodyning is mixing. Okay, super heterodyne is super mixing. There's a block schematic of it. You got an RF antenna. Bring it in, micro, just tiny bits of power coming in there, right? Just itty bitty bits. So we amplify it with an RF amplifier. Then it goes to a mixer that's got a local oscillator input. Then it goes to a filter to straighten it all out. Then it goes to an IF amplifier, which is an intermediate frequency amplifier. Then it goes to a demodulator. Once the demodulator takes the modulation from the signal and goes, this is what they're trying to say, and then it goes to an audio amplifier, which drives a speaker, whether it's in your headset or the speaker on the radio. Okay, so basic super heterodynes. Incoming radio frequency, RF signal, is mixed or heterodyne with a local oscillator to produce an intermediate frequency signal, or IF. The super heterodyne means the local oscillator frequency is higher than the input frequency. And it's easier image rejection, so the IF signal is amplified and filtered. Sharp, narrow filters reject noise signals close to the desired frequency, so they only let in the stuff we're looking for. If the IF amplifier in an FM receiver includes a limiter stage, the amplifier stage, which is an amplifier stage with high gain, so that signal flat tops, so eliminating amplitude variations. It's got a diode clipper circuit, and so none of that was yellow, but it's good information. Managing receiver gain. RF gain and automatic gain control, AGC. So you've got RF gain, you've got audio gain, you've got automatic gain control. There's all kinds of different things. So RF gain and automatic gain control. RF gain, start with the RF gain set to maximum, which is the highest sensitivity. So that is the microvolts coming in, you're boosting them as much as you can. Okay, I don't need that much. You turn it back. Adjust down for comfortable listening, lower noise, because you're amplifying the noise as well. Audio frequency gain or volume controls the audio level to the speaker or headphones, so that's audio frequency gain, also known as volume. RF gain controls the strength of the radio signal entering the receiver, and it's used to limit or attenuate very strong local signals. Usually operated in the full open position, the RF gain, and then you back it off.
And especially in the low bands, like once you get involved in HF, if you're on 80 meters, even 40 meters, sometimes the noise level in the background is so high, it gets obnoxious. Well, if the signal strength from the other station is strong enough, you can back off that RF gain, get the noise level down, and still hear the station just fine.
Yeah. Just don't forget to turn it back up when you go looking for a next one. You may not hear them. Okay, automatic gain control, AGC. It is in yellow. Automatically limits the incoming signals during signal voice peaks. Prevents peaks from capturing the receiver and limiting reception of lower level portions of the incoming signal. It's fast setting for CW, slow settings for SSB and AM. Signal sideband and CW FM switch sets the amplifier for proper operation in selected mode. AGC, varying the voltage used to adjust the gain of RF and IF amplifiers. So it's automatic gain control. It's using the amplifiers and giving them less voltage so that it allows less gain coming through the transistors of the or the tubes. AGC voltage is measured by S meter. S stands for signal strength. Turning down the RF gain increases the S meter reading. S meter is calibrated in S units. S meter is in yellow. In transmitters, it indicates the output power or other functions as selected by switch setting. So I'm transmitting, and there'll be either a needle moving or a set of dots on an LCD screen indicating how much of the available scale I'm putting out in power. In receivers, it indicates signal strength. So when I let off the push-to-talk and I'm listening to you talk, either my little dots across the bottom of the screen will go, a certain level up, or my needle will go up to a certain level. Sometimes the digital ones will actually have numbers on the scale. Sometimes they'll just have a number of dots, and you gotta know, about what that is. The S meter and meter range in S units of S1 through S9, with S9 being the strongest. And then there are values. I also have decibel readings over S9 to cover very strong signals. So sitting in my house on the Roxanne repeater, which is about 3 miles away, anybody that I talk to on the system has an S meter reading of 60 dB over S9, because I'm reading the repeater's output, not their input. Okay, not their transmission.
That's the deceptive part about repeaters. When
Yes.
somebody asks for a signal check on a repeater, regardless of how they phrase it, what they're actually looking for is how's their audio meter.
Yeah. KG7TU, oh, hey, can I get an audio report, audio check? Hey, can I get a signal report? And somebody comes back with, yeah, you're 5'9". Laugh.
You know they don't understand the system.
Because you cannot be 5'9" on a repeater, because you're only hearing the quality coming out of the repeater, the signal strength out of the repeater. One S unit is a 6 decibel difference in input voltage. So what's coming into my antenna and into the radio, if I go from an S1 to an S2, I got twice as much power coming in to get the S2. And then another doubling of the 2 to get the S3 and on to S9. S9 is 50, what is that? Microvolts.
And that's the only calibrated point on your meter.
Okay, here we go, S meter values. Microvolts, okay, how much is a micro? How many zeros?
6.
Let's see, I think it's up there. S9 is 50 microvolts. S8 is going to be 25 microvolts. S7 is going to be half of that, 12.5 microvolts. S6, 6 1/4. S5, half of that, 3 1/8. S4, 1.5 roughly. S3 is down to 0.78 microvolts. And we're going to have it 2 more times, aren't we? S2 is 0.39 microvolts, and S1 is 0.19 microvolts. So we're already having these zeros, and now we're getting some more. That is of 1 volt. Not a whole lot of juice. Now, a lightning bolt that hits your neighbor's tree is 1,000,000 volts real close. And it's going to send out an electronic signal.
And that burst is really nasty.
It is so nasty that when there's a cyclone in the South Pacific and you've got a waterfall, you can see every lightning strike. And there's a line across the entire band. Okay, so that's how little the power coming in is.
And we keep striving as receivers get better and better and better.
Oh my God, they're getting.
All of a sudden, your usable content is down below 1 microvolt.
Yeah, it's
Below 1 microvolt.
Yeah, or 2/10 of a microvolt.
less than that.
Yeah.
Less.
You're talking.
The electrician's
You're
free.
driving down the road. What about static electricity?
Oh yeah,
Yeah.
it's a real issue.
Yep.
You're catching on. You're doing good. That's why we have filtration that is
Yeah.
designed to increase the selectivity to the point that we're looking at a really narrow spectrum.
And that's why we use FM.
Oh yeah.
Yeah. Okay, so if you're out in the country and you turn off all your filters and you're driving down the road and you pass a horse farm, it's got those cute little plastic poles with the little strips of nylon,
They'll grab you,
an
bud.
electric fence. It'll go. You'll hear it. You'll hear it in your AM radio in your car if it doesn't have good filtration. You'll hear it in your FM radio on the handbands. You'll hear it in the FM radio, So these numbers, you're not. These numbers, you will.
Yes.
S1 through S9,
Right.
and then dB over S9. All right, carrier squelch. Squelch mutes the receiver output noise, audio to speaker, when the signal is not present. So there's a background noise, just the
There's always a
garbage.
noise floor.
The garbage that's in the air, yeah, the noise floor. You turn the squelch until it goes, and it might go a little tiny bit more, and it'll stop doing that.
You shut off the noise floor. Now you're listening for signals.
Signals that are stronger than the noise floor. It's used in FM primarily, and open is setting the squelch threshold so that the receiver output audio is on all the time so the weak FM signal can be heard. It is annoying as all get out, but a lot of receivers have a button that is called MONI or MON. You hit that and it opens the squelch completely so that you can listen.
Example. This is squelched. Yeah.
That's
Open
not-
squelch.
Any
Push the button.
signal coming in, it will pick up.
So the advantage of opening it up is if you're listening to somebody on simplex and they have a weak signal,
Yep.
you may only be able to hear that station if you open up the squelch. The squelch is tightening it down enough that that signal will go away.
So I can set the radio for an open squelch, but it means going into the menu and doing a bunch of steps and that kind of stuff. So hitting the button is a temporary way to just listen for that signal.
And if you open the squelch, you're going to probably want to turn the volume down.
Yep.
It's actually easier to hear a weak signal with the volume down and paying closer attention.
So it's another tool you can use, but you won't use it often.
You'll see a ham on a contest, and he'll be like this with the ear cups up against his ears and he's turning down the volume a lot of times so that he can try and pull the voice out of all the noise. He's trying to get the noise below where his brain can process the voice that's in there somewhere. Setting squelch threshold so that receiver output audio is on all the time so that a weak FM signal can be heard is open squelch. Tight allows only the strongest signals to pass through. There'll be somebody trying to talk to you and you got your squelch too tight, it won't listen to them. When they're trying to get in a conversation, the other guy can hear them, but you can't. Might be your squelch, might be he's too far away. Advance the squelch control until the noise just disappears. Basic super heterodyne receivers. Output from the IF amplifier is sent to a demodulator circuit. So the IF amplifier, that's the intermediate frequency amplifier, sends it over to a demodulator circuit so that we can pull out the useful information. The type of demodulator varies by mode. And we got AM uses a product detector or an envelope detector. CW single sideband uses a product detector. And FM PM uses a frequency discriminator or a quadrature detector. FM and PM use the same basic structures. So that's phase and frequency modulation. AM and CW and single sideband can use product detector. Product detector is a mixer fed with output of the IF amplifier and the output of the beat frequency oscillator, or BFO. BFO frequency is at or near the IF frequency. For single sideband, the BFO frequency is set to the carrier frequency of the single sideband signal. So yeah, if you don't have one, can't do that, huh? For CW, the BFO frequency is set to a few hundred hertz above or below the carrier frequency. Okay, filters. A noise blanker works by reducing receiver gain during a noise pulse. So we used to use these with CBs. You'd turn on the noise blanker and it would take out the spark plug wire pulses and the sparks from the spark plug. It'll knock, if you have the noise blanker on, you won't hear that electric fence. It'll take that out. But if you turn the noise blanker off, you'll hear the electric fence. So, if you want to cross the fence and you need to know if it's on, turn off the noise blanker and listen. It's not going ting, ting, ting. Well, it must be off. That's when you send your youngest child over to test it. or your less favorite, because they're all your favorite, but you got a less favorite. Okay. Or your wife.
Only you, Bruce.
I don't have kids, so I can talk like that. All right. The noise blanker can be used to reduce ignition interference to a receiver. Or you drive a diesel truck, then you don't have to worry about ignition noise. All right, filters, noise blanker, still. Example, if another operator reports a variable high-pitched whine on the audio from your mobile transmitter, it could be caused by noise on your vehicle's electrical system being transmitted along with your speech audio. Now, what would give you a variable high-pitched whine in a car?
Motor.
A what?
Your heater motor.
Not
No,
really.
that's
Your motor
gonna,
runs at a constant speed.
that's gonna
By
be a-
variable, he's talking about when you hit the gas and you're accelerating.
Oh, you're talking.
The frequency of the noise is going up. That tells me that it's something in your ignition system.
or the alternator.
Yeah,
The alternator speeds up when you speed up.
yeah.
Your heater can do it, but it's not going to vary.
Right.
It'll vary
It'll be a
only
constant noise.
only if you change the switch position for the fan speed.
Now, it used to do it with points and condensers.
Yes.
But does it do it with electronic ignition?
Yes.
Yes.
If anything, it's worse. They've gone to some pretty great lengths to filter that out and maintain it and keep it into that little computer module. But they've never made it go away.
So in the old days, you might get 30,000 volts across the spark plug. Nowadays, it's way more than that. So that's going to make way more noise. But the filters have also gotten better, and they've had to filter them because they got computers in the car, and those noises would cause issues there.
Yeah, they didn't do it to protect us, I promise you.
Noise reduction is still. Increasing noise reduction levels may cause some of the desired signal to be removed as well, and that can cause distortion. So if you're trying to knock out the noise, you're going to possibly knock out some of the desired part as well. Receiver incremental tuning, RIT.
And that is one of the most useful, constantly used things you will ever find in sideband.
And misunderstood.
Yeah.
Receiver incremental tuning, or RIT control, used to make adjustments if the voice pitch of a single sideband signal seems too high or too low. It's called a clarifier on some radios. That would be anything with the word Yesu on the front. They call it a clarifier. Everybody else, I believe everybody else, calls it a receiver incremental tuning,
Yeah.
or RIT.
Yeah.
Scanning function. This is different now. It's not receiver incremental tuning. Tunes through a range of frequencies to check for activities. You can scan the entire band, or you can scan just your memory channels that are programmed in.
And it depends on the mode that you're in. If you're in a channel mode, if you are in memory mode, and you set that thing for scan, it's going to scan
Scan
the
the
memories.
memories.
If you are in VFO mode, it's going to scan the band.
Okay, weak VHF signals. In order to pull in weaker signals on single sideband or CW when attempting long-distance communication, a multimode transceiver can be used. Also, now this part maybe, an RF power amplifier can be used to increase the transmitted output power from a transceiver.
Do you really want to do that?
Talking about weak signal, single sideband.
Oh, okay.
So when I first started trying single sideband, I had a couple of amps sitting in the shack, the old shack, and they were like, oh, power is everything on sideband. Get as much power as you can out. Oh, okay. Well, I went and hooked it up. It works a lot better, but you're still required by the FCC to use the minimum power necessary to make the communication. So, if you got 1,000 watts in your flower pot, it doesn't matter. If you only need 5, you better be using 5. We'll get to that when we get to regulations. Okay, receivers can be limited to ham bands, or they can cover other parts of the spectrum. General coverage receivers cover a wide area of the spectrum and can be used for shortwave listening. If distorted audio is received from an FM signal, the receiver may be tuned above or below the frequency of the signal.
General coverage. Why would a general coverage receiver be something that you would want to have? The frequency-specific tones available from CCH in Canada and WWB in the US are transmitted on frequencies that are not part of the ham, and they are the best way there is to check the frequency stability of your radio.
The other thing is, if it all goes to heck in a handbasket, anybody transmitting anywhere in there, you can hear them at least. So you can go an AM station, you can pick it up. Doesn't mean it can transmit on them, it's receiving them. If distorted audio is received from an FM signal, the receiver may be tuned above or below the frequency of the signal. Okay, design challenges. Who's going to design a radio? Anybody? I guess we can skip this part. Let's see if there's any yellow. Images, two different frequencies when mixed with the with the local oscillator frequency will produce a signal at the intermediate frequency. The unwanted frequency is called the image. The image frequency must be filtered out by the receiver front end. The farther the image frequency is from the desired frequency, the easier it is to filter out the image. So we want it as far away as we can get it, right? But still find it, because we don't want to put an image out that we didn't find. The local oscillator and other oscillators in the circuit can mix and produce signals at various frequencies. These spurs are some kind called birdies, so it's not like in golf. And it can cause interference to the desired signal. It is unwanted radiation is a design challenge. You don't want RF in the shack. You don't want any radiation that you don't want. The local oscillator signal can leak out through the receiver front end to the antenna and be radiated. Oops, we don't want to do that.
So most synthesized radios that have
Yes.
synthesized frequency will produce those birdies in a very regular spacing. And when you go down the band on HF, you'll hear these bleep, and then bleep, and then bleep, and bleep. And those little spurs are being caused inside the radio. They're not coming from outside. They're part of the radio.
Sometime, now I don't know if this is the same thing, but I'll turn on my 7300 and there'll be a line every X number of megahertz apart.
Yep.
Zip, 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 all the way across the scope.
Yep,
Is that the birdies?
yep,
So that's me.
yep.
That's not good.
It's internal.
All right, double convergence.
Actually, it is, Bruce, because if you pay attention to those birdies and understand what they are and where they are, and are aware if they move, then you know you've got an internal call on your radio.
Ah,
They should be really regular.
should be what?
Really regular.
They are.
Yeah.
Okay, double conversion and triple conversion super heterodyne receivers. Double and triple conversion. 2 or 3 local oscillators with 2 or 3 different sets of IF amplifiers and filters. Why would we do that? Why would we make it that complicated? Because then we can compare them to each other.
Not only that, it's a really good way to keep Joe's fry house and his radio equipment from interfering with your radio.
Yeah.
Because they're out of a whole different set of frequencies.
Because it allows better filtering at lower frequencies. Increases susceptibility to images and birdies though. But there's nothing yellow there. IF filtering, use filter whose bandwidth matches the mode being used. So if you're on a FM signal and you require 6 kilohertz, do you want to use a 500 hertz filter? Wouldn't work very well, would it? You just chopped out everything. The older one, I didn't understand that when I got started either. The older one, 500 hertz, 2400 hertz. What is this? Why do I want the narrowest one. I want the one that cuts out all the noise. Oh, that doesn't work very well.
Nope.
Get out the manual. Oh, that's for CW. Yeah, the best signal to noise ratio, or S/N, is out of your IF filtering. Digital signal processing, part of practically all modern transceivers. Replacing some of the analog circuitry, the procedures convert the analog signal to a series of numbers, ones and zeros. Process the series of numbers mathematically, convert the resulting series of numbers back to an analog signal. Why do we do that? Because computers can do that processing super duper fast. Advantages. Performance allows the signal processing difficult to obtain by analog methods. You can create whatever filter you want if you've got a fancy radio. Flexibility. Functions, options, and adjustments are limited only by the processor speed and memory. Oh yeah. Main uses of digital signal processing. Signal filtering. A wide range of filter bandwidths and shapes can be created, and it is awesome to look at and just tweak the little dials and make it go exactly the way you block out all the garbage. The users can create their own custom filters. It helps with noise reduction. Many types of noise can be detected and removed. The computer goes like, that is an electric fence. We don't want to listen to that. Notch filtering is awesome. Automatically detect and notch out an interfering signal. So that's the notch filter found on many HF transceivers reduces interference from carriers in the receiver passband. So the passband is the part it's allowing through. If there's an interference signal in there from a carrier, it can knock that out and keep the one you want. Audio frequency equalization. Software, oh, here we go. This is good stuff. Software-defined radios. The ICOM 7300 is my favorite because I have one. A software-defined radio, SDR system, is a radio communication system where components that have been typically implemented in hardware, e.g. mixers, filters, modulators, demodulators, detectors, etc., are instead implemented by means of software on a computer or embedded computing device. The ideal SDR receiver would be to attach an antenna to an analog to digital converter. Similarly, the ideal SDR transmitter would be to attach a digital to analog converter to an antenna. Not feasible with current technology. This might be an old slide. We're getting there.
We're getting closer, but
We're
it's still
getting
not-
real close.
Yeah.
So some compromise is necessary. Software, some analog processing is still required. The future is an all-digital radio. Commercial software-defined radios are now available for amateur use, and they are awesome. So these, let's see, these are the old ones. So these are software-defined radios. But this is the one you want. That's an ICOM 7300.
Yeah, they're a nice compromise. I think
That's what makes them so damn popular.
The only thing I don't like about this radio is it doesn't do VHF, UHF. That same radio, capable of doing VHF, UHF, and one other band. So you get 3 bands. It's $1,800 right now. And this one that gives you 6 meters to 160 meters is $950 sometimes on sale. So
Usually running about 1150.
I recommend that one, and I recommend the 991 Alpha, but you don't have to spend that much money to get on HF. Receiver linearity. Just like a transmitter, nonlinearity in a receiver results in spurious signals. It can cause overload, extremely strong signals that can drive the RF preamp into nonlinear operation. Nonlinear is not good. Results in distorted received audio. RF attenuator control. Prevents receiver overload from strong incoming signals. Used in combination with the RF gain control,